right, so this is a continuation of our introduction to vowels. Today we're going to talk about the acoustics of vowels. So if you remember from our previous lecture, we did talk about this as a basic review. For a resonant frequency of a tube open at one end, if you remember that, the formant frequencies are also called resonant frequencies, and that is what you have right here, F1 or R1. And the formulas for those are, remember, the wavelength is 4 times the length of the tube. Length of tube for the first frequency, first resonant frequency, and that's how you got the 4L. And then your formant frequencies 2 and 3 resonate at odd frequencies. At odd multiples, resonate at odd multiples of R1 or F1. That's how you got 3 times C over 4L and 5 times C over 4L. And our vocal tract is similar to the tube being open at one end, right? Although it's not as simple as a tube, it's a complex structure with a lot of constrictions at different levels. So this is an example for a human male vocal tract. The length of the tube, if it's 17 centimeters, the C is given 34,000 centimeters per second. That is your R1, that's your R2, and that's your R3 by using the formula. So R1 equals C divided by 4L. That is nothing but 34,000 divided by 4 times 17, which is nothing but. So these is how I want you to calculate the steps. When I ask you to do this for your lab 2, 68, and that's nothing but 500 hertz. So if I ever ask you the steps for calculation, that's exactly how the steps of calculation should be. For R2, you will say it is 3 times C over 4L. That's nothing but 3 times 500. That's equal to 1500 hertz. R3 is, that's a typo there. If I'm just going to change it, that's a typo right there. So mark that as 5. Okay. R3 is 5 times C over 4L. That's nothing but 5 times 500. That's nothing but 2500 hertz. Okay. So are we clear on this so far? So resonant frequency is the frequency where it vibrates at maximum amplitude, right? And that resonant frequency will change based on the configuration of our vocal tract. We talked about that, our vocal tract. And our vocal tract serves as a variable tract resonator. Okay. So today we're going to talk about how do we understand this. We talked about this source, which is our vocal folds. We talked about our vocal tract, which is our variable resonator. How is this helpful in our speech sound production? How are we going to arrive at vowels? Okay. So this is again a repetition of what we did. Resonant frequencies of the vocal tract are called formants. Vocal tract is a variable resonator. Typically for speech sounds, we're only interested in F1, F2, and F3. Okay. We're going to talk about something called the source filter theory of vowel production today. Since we're talking about vowels, we want to understand how that sound that comes from the level of our vocal folds gets modified at the level of the vocal tract to be able to produce a perceptible speech sound, a vowel sound. Okay. So we're going to talk about 1, the source. 2, we're going to talk about the filter. And 3, that's the output, which is the vowel production. Okay. The source is nothing but our vocal fold vibrations. So we're looking at the level of our vocal folds. Our vocal folds vibrate to produce our fundamental frequency. So the source is vocal fold vibrations. So if you didn't remember this, I keep repeating this in almost every lecture. If I removed my head and kept it on the side and all I had was my lungs and my vocal folds, the sound when my vocal folds vibrate, all I hear is a bzzz, 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 right? If I added this vocal tract on top of it, the different configurations of the vocal tract, whether my tongue is high in the mouth or low in the mouth, whether my lips are protruded or spread, all of these are going to change what we hear as different speech sounds. So the filter that we talk about is going to be the resonance of the supraglottic or the vocal tract. Supraglottic meaning above the glottis or above the vocal folds. Okay? So we're going to talk about the source, we're going to talk about the filter, and how that output is going to be transferred. Now, I'm going to move away from the slides for a second. I'm going to open up a Word document and I'm going to talk to you about the source filter theory of speech production. Okay, so that's what we're going to talk about. If you look at it, that's the source, that's the filter function, and that's the output, a combination of the source. Oops, sorry, that's not where I wanted that. That's, if you add those two, your output is going to be that. Okay, so this, if you remember, that's a spectrum. Okay, this is frequency and this is amplitude. All right, so that's a spectrum which has that first frequency is your fundamental frequency and these are your harmonics. This is your source. Okay, this is where your vocal folds are going to be vibrating to produce our fundamental frequency, right? Okay. The next what we're going to talk is about, we're going to talk about the vocal tract. Source, vocal folds. So. Okay. These frequencies that you see is the formant frequencies or the resonant frequencies. This formant frequencies depend on configuration of the vocal tract. Okay, if you remember, we talked about this. The resonant frequencies or there are natural frequencies that are present in any system, and those natural frequencies will help us in identifying what the resonant frequencies are in the vocal tract, right? So these frequencies, the R1, R2, and R3, are the natural frequencies that will vibrate with maximum amplitude when the source hits the vocal tract. So that is my source at the level of the vocal fold. If I add it through, if I send that source, spectrum, those are my F1, F2, and F3. Now these F1, F2, and F3 are the natural frequency of vibration when an air from the source passes through that. My output is going to be okay, that's going to be my output. How did we arrive at this output? So the source, which is at the level of the vocal folds, the sound source, passes through my vocal tract, which is the filter function. It has natural frequency of vibrations for that configuration, F1, F2, and F3. When that source passes through, some harmonics that are matching at these peaks will get amplified, and some harmonics that are not near the peaks will get dampened, resulting in that output. And this output is a particular vowel sound. Okay. All right. So the source, how is the source determined? The source is determined by the rate of vibration of the vocal folds. So my vocal folds are coming together. For a male, it comes together 100 times a second. For females, it comes together 200 times a second. So source is determined by the vibration of the vocal folds. The filter frequency is determined by the vocal tract configuration. So if we were to consider a particular vowel sound, our vocal tract configuration is going to be changing. So if I say E, my tongue is in the front, it's in high position in the front, and the back of the tongue is lower, and my lips are not pouted, it's spread out. So that vocal tract configuration has a certain frequency with which when the air comes through, it has certain resonant frequencies, and so the harmonics that pass through those resonant frequencies will get amplified while the other harmonics will get dampened. Okay, that's why it's called the filter function, because it's filtering certain frequencies and sending more other frequencies through the vocal tract. Okay. So this is the same thing that I said. So to reiterate, we have the source, which is your vocal folds. Then you have the filter function. Vocal folds, it has a fundamental frequency plus harmonics. Your filter function has peaks, and those frequencies are determined by the vocal tract configuration. When the source passes through the filter, that is basically when the air from the vocal folds passes through this configuration for a particular speech sound through your vocal tract, it results in certain harmonics amplified and certain harmonics dampened, giving this unique configuration of a speech sound. Okay. So that isn't just about the acoustic theory of vowel production. You have a source, you have a filter function. Your source is your vocal folds. Your vocal folds have a certain frequency of vibration. It has a fundamental frequency, which is what is determined by the average number of vibrations, and it has harmonics. When these harmonics and fundamental frequency passes through the filter function are nothing but peaks, which has those natural frequency of vibration, and when those air from the source passes through those natural frequency of vibrations, the peaks, around the peaks where the harmonics are, those harmonics will get amplified, and those harmonics that are not near the peaks will get dampened, resulting in this unique speech output that is our vowel sound. Okay? Now, some of the things that we need to understand, that for a particular individual, say for me, my sound source is constant. Why do I say that? My vocal folds always, this is for me, for Miss N, my vocal folds always will vibrate around 200 cycles per second. My sound source is always going to be constant. So if I go from I, U, right? When I change the shape, that is how I'm changing from the vowel A to E to U. I am changing my resonator, which is my vocal tract, and I make different speech sounds. But that sound source for Miss N is always constant, 200 cycles per second. Okay. So that is to tell that source and filter are independent of each other. Meaning, if I change the source, my filter does not have to change. So for example, if I go it's the same all I changed was I changed my source. My source varied from my regular pitch to a slightly higher pitch to a high pitch. When I changed that pitch, which is when my source changed, my fundamental frequency changed, when that changed, my that was an my still stayed the same, my vocal tract configuration. So I'm still perceiving the same speech sound even though my source is different. Now, if I keep my source constant, which is my vocal fold vibration, and I go look, I can change my vocal tract configuration keeping the same fundamental frequency. Okay. A key thing that I need you to understand is the length is inversely proportional to the frequency. If you have performed the exercise from last week's lecture, you should have derived that relationship by now. As the length of the tube, in our case, the vocal tract, increases, it decreases the formant frequencies. Okay. If you have done my Lab 2, or if you have even seen the previous lecture, and if you have done the assignment or the class exercise that I asked you to and derive the relationship, that's the relationship that you should derive. As length of the tube or your vocal tract increases, it decreases the formant frequencies. So smaller the vocal tract, greater the resonant frequencies. So if you think about males versus females versus children, who has the smallest vocal tract? Kids, right? Children. So children have the greatest formant frequency compared to females, and females have more higher formant frequencies or resonant frequencies than males. Males in general have less decreased resonant frequency, lower resonant frequencies. Let's put it that way, lower resonant frequencies. Okay. So what are the take-home points from this slide? The take-home points from this slide are the source and filter function are independent of each other. You can change one and the other will stay the same. It doesn't have to be dependent on each other. Second, any changes in length of the vocal tract is going to affect the formant frequencies. Greater the length of the vocal tract, lower the formant frequency. Males have a greater vocal tract, so their formant frequencies in general are lower, and kids have the highest formant frequencies. Okay, this part is very, very important because that's going to definitely be on your midterm, and also it's going to be important to understand that to do your lab 2. Okay, so now we talked. Let's think about this. We talked about formant frequencies. You're like, yeah. She talked about F1, F2, F3. She talked about calculation about F1, F2, F3. She talked about the acoustic theory of vowel production, where she said something about the source. Then she talked about the filter function, which had those peaks. And then the final output was this vowel sound. What does this all mean? Right? You're sitting there and I'm thinking, I can't get any sense of it. Now, how do you know when I am saying ah, I'm saying ah? How do you know when I'm saying the vowel sound E, I'm actually saying E? This formant frequencies are the ones that help in the acoustic and perceptual identification of vowels. What we hear or what we see on a spectrum or a spectrogram is these formant frequencies. That pattern that we find, whether it is F1, what is the F1? What is the F2? What is the F3? What is the difference between F1 and F2? Or what is the space between F2 and F3? That is what is called the F pattern, and that F pattern is the one that is very, very important to perceive the correct vowel and to acoustically identify on a spectrum or a spectrogram what that particular vowel is. Okay, the amplitude of the peaks is not important. It is not. Remember, even when we talked about periodicity, in periodicity it's the frequency that is important and not the amplitude. Similarly, in the formant frequencies, we are talking about the F pattern, the gap or the distance between the frequencies, and the amplitude does not really matter. Okay, so the acoustic and perceptual identification of vowels is based on F pattern. So if I asked you in your midterm, give me one key point for, or give me one pattern that helps us in the acoustic and perceptual identification of vowels, you have to say it's the F pattern. Okay. All right. So this is what I've been talking about, the F pattern. I'm going to be talking about 3 vowels shortly. We're going to be talking about the vowel E, then we're going to talk about the vowel A, and then we're going to talk about the vowel U. Okay. F1, F2, F3. F1, F2, F3. Same way here. But look at the pattern. F1 is low. F2 is very high. Look at the difference. F2 minus F1 is about 2000 hertz. That's a huge F difference between, but not so much difference between F2 and F3. Here, they are very close together, but F1 is really high. And this, not so much different. These both are lower and great difference. This is what I'm talking about, the F pattern. What is the F1 frequency? What's the F2 frequency? What's the F3? What is this pattern between F1 and F2 and F3? This F pattern is what helps us in the perception of these vowel sounds. Do you need to know these numbers? Of course you need to know these numbers. You have to know what the vowels, what the form and frequencies are for each of these vowels, and you will understand more about these vowels when we talk shortly about them. But you need to know these numbers, what the F1 for E, A, and U is, what the F2 is, and what the F3. F3 is an approximation, but you really need to know the F1 and F2. Okay. So let's talk about the vowel sounds. As I said, I'm going to talk about 3 vowels. Let me show you what the vowel quadrilateral looks like. You see this? All of these are the vowels in your English language. Okay? This is called the vowel quadrilateral. So we're going to be talking about 3 vowels, the E, the A, and the U. They are extremes in the vowel production, and so we're going to try to understand what these extremes mean and how we can help understand the form and frequencies of these. Okay, so this is again a repetition. This slide is just a repetition of our acoustic theory of vowel production and how the source and transfer function is also called the filter function, are independent of each other. So the final output, the vowel, is an accumulation of your sound source, that is from the vocal fold vibration, which has the fundamental frequency and harmonics. That fundamental frequency and harmonics, when it's released from the vocal folds, it comes into the vocal tract. This vocal tract has a special configuration for each speech sound. So that, and those special configurations have certain frequencies, also called the formant frequencies or peaks, that will vibrate with maximum amplitude when air passes through them. So the source from the vocal folds will pass through this configuration of the vocal tract, amplifying certain harmonics, which are closer to the peaks, and dampening the rest. And the final output is going to be your vowel production. Okay, again, source and this filter function are independent of each other. You can change your fundamental frequency and still produce the same vowel sound. For example, that's the same vowel sound in 3 different frequencies. But I can keep my source constant, which is keeping my fundamental frequency constant, but I can change my vocal tract and make different speed sounds. So for example, E, U, that's my same source, but different vocal tract configuration. So I want you to understand that source and filter function are independent of each other. They do not depend on each other. If one changes, the other does not have to change. It is very, very important concept. This is a definite question in your midterm. So we talked about the vowel quadrilateral. You should know how to draw the vowel quadrilateral. Okay. Those are the 3 extremes. The dimensions are going to be high to low, front to back. Those are your basic dimensions or parameters of your vowel quadrilateral. Your tongue height and your tongue advancement, whether it moves from front to back or your tongue goes from high to low. Okay. So what does this tell us? E is a high front vowel. A is a low back vowel. And U is a high back vowel. Okay, so we're talking about all extremes in the vocal tract configuration. All right, so that is the same thing. Now, this is the vowel quadrilateral right here, right? I want you to pay attention to this graph right here. This is F2 and this is F1. So you see the relationship between F1, whether it's low or high, low, and F2 is high for E. Low F1, high F2. Keep that in mind, and I'll come back to this in just a little bit. Okay, I'm going to come back to talking about the relationship between F1 and F2 based on the tongue position, the tongue height, the lip movements. Okay. This is just an example of the vowel sound. The lip is closed in E and it's open in A. Okay. I'll come back to the spectrogram in just a second. Let's talk about how these different vowel sounds are being produced. Okay. Remember I said the E is a high front unrounded vowel. Now, let's produce E. I want everybody to go, as you're doing this, E, and I want you to think about how your lips are, where your front tip of the tongue is, where your body of the tongue is, the dorsum, E, or the back of your tongue, okay? E. When you think about this E has a lot of high frequency energy. And why do you think that is there, okay? When you talk about the E, what happens to your mouth? The oral cavity is the space before or in front of the tip of the tongue. Okay, if you were to think about that, your oral cavity is the space that is in front of your tip of the tongue. How much space do you have in front of the tip of the tongue? A very small space. You have a really small space. Okay. Why do you have a small space? Because the tongue is moved forward to the alveolar ridge. Alveolar ridge is the space that is behind your teeth. If you have looked at the lectures, Vowels lecture posted by Mrs. Basham should be talking about the production of these speech sounds, right? Vowel sounds. So the tongue is moved forward to the alveolar ridge behind your teeth. The tongue mass occupies most of the oral cavity, okay? And there is less space anterior to the tongue for vibration, which means smaller oral cavity. So think about this. I want you to close your eyes and go E, and I want you to see how your tongue is, where the dorsum of your tongue is, where your tip of the tongue is, how much space is front of the tip of the tongue. So that the space that is in front of the tip of the tongue is the oral cavity. Okay, so the smaller oral cavity happens during E. Okay. It's the reason why it's called a high rounded tongue is high. It's fronted. There is no lip protrusion. You see that? That is your lip. You see how the tongue is high. And that is your pharyngeal cavity. So it has an open pharyngeal cavity and small oral cavity. Okay. So the first formant, when we talk about F1 is going to be lower because of the large pharyngeal cavity in the back and the small mouth opening. Okay. F2 and F3 are both going to be higher in frequency because of the shortened oral cavity, and the shortened oral cavity resonates at higher frequency. This is where the length is inversely proportional to frequency is very important. Small oral cavity, that is smaller length of the oral cavity, resonates at higher frequency. Okay. Now, you're sitting there and thinking, okay, why is the pharyngeal cavity large and why does it have to lower the F1? If you go a few slides forward where I talk about the relationship between resonant frequency and cavities, F1 always depends on the size of the pharyngeal cavity and mouth opening. Okay. F2 is always going to depend on size of the oral cavity. Now, how? This is a general rule. The rule was found out by doing some studies, radiographic studies, where they found similar to this thing that you did. These are radiographic studies that were done by scientists, and they have found how the space variations resulted in changes in what kind of form and frequencies, and they have arrived at this general rule that the size of the pharyngeal cavity and your mouth opening or mouth constriction will determine your F1, and the size of the oral cavity will determine your F2. Now, we already know that the length of the tube is inversely proportional to frequency. So anytime there is a large pharyngeal cavity, there is going to be lower F1. Okay. Mouth opening, small mouth opening, lower F1, large mouth opening or an open mouth, higher F1. Now, is there any way to get around this? Probably not. This is how you need to remember this. These were studies that have been done by scientists that have looked at radiographic studies, measured the different tongue positions, measured the constrictions, measured the gap in all these cavities or space in all these cavities, and have arrived at certain rules, which are these, that helps us in identifying the different vowels. So for the purposes of E, the first formant, okay, is going to be lower, because if you think about the production of the E, there's going to be a large pharyngeal cavity. If you think about the lips or the mouth, there's going to be a small mouth opening. But the oral cavity, that is the space that is anterior to the tongue, the tip of the tongue, is the space that is very small, because the tip before the tip of the tongue, there's very little space, and it resonates to higher frequencies, so F2 is going to be high. So if you look at the numbers right here, lower F1, really high increased F2. Look at that space. That is called the F pattern, which we talked about earlier. Okay. This is another thing that talks about source and filter independent. Okay. I am going to skip slides 20 and 21 because these again talk about source and filter are independent. All right, this is a visual representation of the vowel E. This is a spectrum. This is a spectrogram. Okay, again, notice that F3 minus F2 is small, F2 minus F1 is large. That is the F pattern that is unique to the vowel E, that helps us in the acoustic and perceptual identification of the vowel E. So let's reiterate, okay? We initially talked, as soon as I started the lecture, I talked about the acoustic theory of vowel production. The acoustic theory of vowel production, I talked about the source, which is the vibration of the vocal folds, which has fundamental frequency and harmonics. Then I talked about the filter function. The filter function is the function that has peaks, which are the natural frequency of vibrations that will get amplified when a certain air passes through them. And those are special vocal tract configurations. When your source passes through the filter function, your output is a vowel sound. Those vowel sounds have certain form and frequencies where the harmonics are amplified, and harmonics that are not near those peaks are going to get dampened. That is called the acoustic theory of vowel production. The source and the filter function are independent of each other. And we talked about this. You can have a source constant, but you can change your vocal tract configuration to make different vowel sounds. You can keep your vocal tract the same, but change your vocal fold vibration, change the different pitches, but have the exact same vowel sound. So the source and filter are independent of each other. Then we said, why is this all important? Why do we talk about form and frequencies? Why do we talk about source? How these form and frequencies are going to help us? And how this acoustic theory all makes sense? It all makes sense because these form and frequencies are the ones that are very, very important in the acoustic and perceptual identification of different vowels, right? Acoustics meaning the study of sound. We talked about the F pattern, meaning how is a pattern between F1, F2, and F3. Whether there is a large gap, whether there is a small gap, whether F1 is higher, F1 is lower. That pattern is what helps us in the unique identification of different speech sounds. Then we talked about a particular vowel sound, that is the E, right? We talked about the vowel quadrilateral first. In the vowel quadrilateral, we decided we're only going to talk about the extremes of the vowels of vocal tract configurations that involve the E, the A, and the U. The EE is a high front unrounded vowel. In the vowel quadrilateral, we talked about the two basic parameters, the tongue advancement from front to back, or the tongue height from high to low. So vowel E is a high front unrounded vowel. We talked about this main cavities or the rules that helps us in identifying F1, F2. F1 basically depends on the size of the pharyngeal cavity and the mouth opening. And F2 depends on the size of the oral cavity. As I said, there is no way to get around this. These were done by radiographic studies. So you need to understand also this is where the rule comes in. As the length of the tube increases, the Forman frequency decreases or lowers. So if the size of the pharyngeal cavity is large, your F1 is going to be lower. If the size of your oral cavity is large, your F2 is going to be lower. Remember this, and that's how we studied E. In E, we talked about, let's reiterate, it's a high front. So the space anterior to the tongue is the oral cavity, which ended up being small. And since oral cavity influences your F2, we had a high F2. The back, the pharyngeal cavity, was large and hence lower F1. Also, the mouth opening was small, resulting in lower F1. So far, so good. That's the production of E. Then we talked about the visual representation here. We observed the F pattern. Okay, so anytime you know E has a lower F1, really high F2. And I'm going to give you a table at the end of these three vowels that will help you remember the Forman frequencies. Now, the next vowel we're going to talk about is a low back vowel. Think about the position. I want you to again close your eyes. Produce the vowel sound See where your tongue is. See how your jaw lowers, okay? And how your oral cavity is. When you say the oral cavity is large, okay? The oral cavity is large because you are lowering the tongue by lowering the jaw and actively depressing the tongue. So go check where your tongue is. Put your hand in your mouth. I'm doing that right now. And go You can do one of two ways. You can just lower your jaw and go or you can go really actively depress your tongue and go Okay, this oral cavity becomes large. Now what happens to the pharyngeal cavity? The pharyngeal cavity, your tongue, it's a low, right? And it's back wall, right? It's a back wall, so your tongue is occupying the back of the cavity, your pharyngeal cavity. So your pharyngeal cavity becomes small. What happens to your mouth opening? Your mouth is completely open. So you have, what are the characteristics? You lower the tongue, so your oral cavity is large. Oral cavity does what? It influences your F2. So which means if it's a large oral cavity, decreased F2. Remember, length is inversely proportional to the frequency. Pharyngeal cavity is small. And mouth opening is large. What happens? These two influences F1. So this F1 is going to increase F1. And this is also going to increase F1. So has around 700 Hertz is your F1. 1090 is your F2. That's lower compared to E. And greater than 2200 is your F3. Okay, there. All right. Does that make sense? You see how the cavities are very important in determining what the F1 is going to be. Think about the production. Think about the cavities that influence and how those cavities influence the Forman frequencies, and you should be able to say that. Okay? So we saw E and we saw A. A is low back wall, right? Okay, and it's really open in the front. So you have a small pharyngeal cavity, large mouth opening influences F1, higher F1. And you have a large oral cavity influences F2, so it lowers the F2. All right. The third vowel that we're going to see is a high back rounded vowel. Ooh. So let me draw the even in your sleep, you should be able to draw your vowel quadrilateral. Okay. All right. high back rounded vowel oo, articulated with the dorsum of the tongue, dorsum meaning body of the tongue, raised towards the roof of the mouth, near the juncture between the hard palate and the velum. So just do it. You know, these are all technical terms. Just go ooh, ooh. You're increasing your vocal tract by protruding your lips. Remember that. When you do ooh, you're protruding your lips. So what are the effects of doing this ooh sound? Okay. What does the protrusion of the lips do? It increases the overall length of the vocal tract. In general, when the length of the vocal tract is increases, it uniformly decreases all the form and frequencies. So you will think about when you compare that overall, when you look at the form and frequencies of ooh, they're going to be lower in general. Okay. When it raises the tongue dorsum, pulls the bulk of the out of the pharyngeal cavity, your pharyngeal cavity is going to be large. When your pharyngeal cavity is large, it resonates to lower F1. Okay. It lengthens the oral cavity and then it helps in the lower F2. Okay. All right. So if you think about ooh, you're lengthening the overall vocal tract by protruding the lips. So it uniformly lowers all the form and frequencies because this is the relationship. Length is inversely proportional to frequency, right? Then you also have this dorsum, which is kind of high up in the mouth. So it opens up your pharyngeal cavity. When it opens up your pharyngeal cavity, it lowers the F1 form and frequency. And then finally, what it does is this lengthened oral cavity, because of the protrusion of the lips and the tongue being high up, it lowers your F2. Okay, so those, if you see in general, those are decrease, decrease, and overall they're decrease compared to A, E, and U. So let's write E, A, U. Let me make sure before I go to the next. Okay, before we go there, E, A, U. F1, F2, F3. F1 is lower, F2 is very high, and F3, I'm going to just leave F3 for now because we'll concern about F1 and F2 for the time being. High, and this is low, and this is low, and this is low. Okay, compared to this, that's what it means. All right, now let's talk about pharyngeal cavity, mouth opening, and oral cavity. Pharyngeal cavity, F1, mouth opening, F1, F2. Pharyngeal cavity is large, mouth opening is small, oral cavity is small. Pharyngeal cavity is small, mouth opening is large, oral cavity is large. Pharyngeal cavity is large, mouth opening is small, and this is large as well because of protrusion of lips. I know I kind of probably just murmured while I was writing there, but I hope this table will help you clarify the combination of the F1 and F2 and how those different positions, F1, F2, and F3, will help you identify those vowels. I'm going to pull up my notes to make sure I have written everything right on that table. Okay, there we go. All right, and then let's just add one more. There's one thing that I want to add is tongue position. Tongue position is high, tongue position is low, tongue position is high. Okay, that pretty much talks to us about the different vowels that we have talked, and see how the pharyngeal cavity, the mouth opening, the oral cavity, and the tongue position have a difference or have an implication on the F1 and F2. Okay, so we talked about the three vowels, E, A, and U. We talked about the production of these three vowels, how it alters the pharyngeal cavity, the mouth opening, and the oral cavity. The two spaces in our vocal tract are the pharyngeal cavity and the oral cavity. The pharyngeal cavity is related to the form and frequency 1, and the oral cavity is related to form and frequency 2. Larger spaces resonate to lower frequencies. So if your pharyngeal cavity is large, your form and frequency 1 is going to be lower. Okay? And the mouth opening also is related to F1. All right? You do have to remember the numbers, because those numbers are what you're going to use in identifying spectrums and identifying spectrograms that I give you in the exams, even for your lab assignments. Okay. I want you to kind of think through this. I want you to take a break here, kind of solidify these concepts. I want you to make sure that you understand what these concepts are, what acoustic theory of vowel production is, what the different vowel sounds are, and then be able to use this information in how these form and frequencies differ, and how these form and frequencies, the uniqueness of the F pattern helps us acoustically and perceptively identify the different vowels. Okay.